Hi, I am Clara Lacroce, and I will present the paper Optimal Spectral Norm Approximate Minimization of Weighted Finite Automata. This is a joint work with Borja Balle, Prakash Panangaden, Doina Precup, and Guillaume Rabusseau. In this paper, we tackle the approximate minimization problem to find an automaton that approximates the behavior of a given WFA while being smaller in size. This is particularly relevant when we are interested in doing model compression. For example, to make the model computationally less expensive or easier to interpret. Here is our contribution. First, we study the approximate minimization problem for WFAs, leveraging their connection with Uncle matrices. Then, we provide a closed-form solution for a class of WFAs over a one-letter alphabet by establishing a correspondence between the parameters of a WFA and the coefficients of a complex function. Finally, we propose an algorithm that returns the unique optimal spectral norm approximation of a given size in O of n cube time. The first important decision to make when doing approximate minimization is how to measure the approximation error. We choose the spectral norm, which is the biggest singular number of the Hankel operator associated with the model, due to some of its desirable features. First, it is not model-specific, so it is transferable and applicable to different classes of models. This is not as relevant when minimizing WFAs with WFAs, but it is important for future applications of this method, like WFA extraction from recurrent neural networks. Second, we can find an optimal WFA producing the minimal error in this norm, and this can be done in a computationally efficient way. In particular, this is possible because the use of the spectral norm allows us to ground our work in the fundamental results of AAK theory, a theory of complex function approximation. We start by recalling the definition of weighted finite automata. A WFA over an alphabet sigma is characterized by two vectors, the vector of initial and final weights, and a transition matrix defined for each character of the alphabet. In this work, we will only consider WFAs with real weights. In this case, the WFA is computing a function assigning a real number to a sequence. An example of weighted automata are generative probabilistic automata, in which the function computed is a probability. The mathematical object at the base of our analysis is the Hankel matrix. This is a bi-infinite matrix with rows and columns indexed by strings in sigma star. Each Hankel matrix H is associated to a function from the set of sequences to R. The entry indexed by P and S is given by the value of F on the concatenation of those strings. This little example illustrates the Hankel property characterizing this matrix. Given two pairs of strings, if their concatenation produce the same string, then the value stored by the matrix at those indexes is the same. Finally, a function over strings is computed by a WFA if and only if the rank of the corresponding Hankel matrix is finite. In this case, the rank is the number of states of the minimal WFA computing F. As we can see, the Hankel matrix stores a great deal of information about the WFA. Our idea is to reformulate the minimization problem of the WFA in terms of the corresponding Hankel matrix. This way, instead of minimizing the automaton, we minimize this Hankel matrix. A well-known theorem of Young, Eckert, and Schmidt states that the best rank K approximation of a matrix is obtained by truncating its singular value decomposition, and the error in this case is given by the singular number of h at position k plus 1. Unfortunately, we cannot use this approach, as the truncated SVD does not necessarily satisfy the uncle property, which is necessary to recover a WFA. So what happens if we enforce the uncle constraint? The quite surprising answer is that the achievable error does not change. Using AAK theory, we can actually find the best approximation within the class of uncle matrices. To introduce AAK theory, we will work in the setting of a one-letter alphabet. This way, the set of strings sigma star can be identified with n by associating to a string the number of times the single letter appears. In this case, we can look at the operator between sequence spaces associated to the uncle matrix through the canonical basis, and we will call it the uncle operator. We consider now sequences over Z by embedding the space of square summable sequences L2 of n into L2 of Z. As mentioned in the introduction, the AAK theory is a set of results concerning complex functions. So we need to find a way to go from sequences to complex functions and vice versa. We do this by applying the Fourier isomorphism. Given a sequence, we can associate with it the function obtained by attaching to each an element of the basis of the complex function space. On the other hand, to associate a sequence to a function f, we can simply take its Fourier expansion and the sequence of its Fourier coefficients. Now we obtain a natural partition of the space of square integrable complex functions on the unit circle. On the one hand, we have the Hardy space containing functions having only positive Fourier coefficients. On the other, we have the negative Hardy space having only negative Fourier coefficients. So now we can consider a complex function phi, and we define an operator that we will also call uncle operator that now acts between Hardy spaces. What is very important here is the relation between the function phi that we call symbol and the uncle matrix of this operator. The entries of H are defined using the negative Fourier coefficients of the symbol. We remark that the symbol is not unique. Phi is a symbol together with any function having the same component in the negative Hardy space. To summarize, we start with a function f that is computing by a WFA over a one-letter alphabet. We then consider the uncle matrix with entries depending only on the sum of the coordinates. Now, the same matrix can be interpreted with respect to another function, a symbol. And the entries depend now on the negative Fourier coefficients of the symbol. So, given a uncle matrix, we can choose one of those two interpretations, and the corresponding functions are related. We can see this in an example. We consider a WFA with two states over a one-letter alphabet. We have the vectors of initial and final weights, the transition matrix for the single letter, and as we can see, the WFA is computing a probability. So we actually have a generative probabilistic automaton. Now we can use F to fill the uncle matrix. This uncle matrix can now be interpreted in relation to a symbol that we can compute. And we see that since we only have access to the negative Fourier coefficients, we don't have an expression for the full function, but only for its projection in the negative Hardy space. Now, using the value in the uncle matrix, we obtain a function that we will later refer to as the rational component. We are now ready to state the AAK theorem. Earlier, we said that the best approximation of rank at most k is attained by truncating the SVD, and we have an approximation error equal to sigma k. Now AAK theorem tells us that the same error can be attained when we are looking for the best approximation within the class of uncoiled matrices. The original AAK theorem is actually stated for operators, and we have that the unique best rank K approximation of a compact uncoiled operator with symbol phi is given by a rank K operator with symbol G. We see that in one case we are looking at the spectral norm of the matrices, in the other at the operator norm of the corresponding operators. In practice, what we are going to use is a version of the AAK theorem stated for the symbols. In fact, this version gives us a constructive way to build the best approximation. In this version, phi is the symbol of the original uncoiled operator, and the bound is expressed in the infinity norm. The theorem states that there exists a function c such that the infinity norm is equal to sigma k. According to the theorem, c can be written as the sum of two components, one in the infinite RD space, which means that it only has positive Fourier coefficients and it is bounded around the unit circle, and a component g that is a rational function with k poles inside the unit disk. So now what happens is that g, the rational component, is actually the symbol of the best approximation that we are looking for. This means that we have a way to find the best approximation for our original uncoiled matrix. So now we are going to apply this for our actual contribution. So in our setting, we assume to be given a minimal WFA with n states, uncoiled matrix H, and a target number of states k smaller than n. Our objective is to find the optimal spectral norm approximate minimization, meaning a WFA A hat of k with k states and matrix G, such that the spectral norm of H minus G is equal to sigma k. To solve the problem, we will require a few assumptions. The first one comes from the fact that to use the Fourier isomorphism, we need to embed sigma star into Z. To guarantee that this is possible, we assume that sigma is a one-letter alphabet. If sigma had more than one letter, we would have a non-abelian structure that cannot be embedded into Z. Then, we need the operator H associated to the matrix of the original WFA to be compact. This is because the constructive proof of the AAK theorem holds only for compact operators. To check that the operator is compact, it is enough to show that it is finite rank and bounded. Since we are dealing with an operator arising from a WFA, we know that it is automatically finite rank, with rank equal to the number of states. On the other hand, to guarantee boundness, we need to assume that the spectral radius of the transition matrix of the WFA is smaller than 1. This means that the eigenvalues of the transition matrix need to have modulus smaller than 1. An example of weighted automata satisfying these conditions are generative probabilistic automata. So here is how we are going to proceed to solve the approximate minimization problem. We suppose we are given a WFA with n states. First, we want to find a symbol phi for the WFA. To do so, we will consider the uncoiled matrix of the WFA and the dual interpretation illustrated earlier. Second, we are going to use the symbol formulation of the AAK theorem to find psi, where we recall that psi can be written as L plus G. Third, we need to extract the rational component G. Finally, we will find a WFA representation of G meaning the WFA having Hankel matrix corresponding to the symbol G. Okay, so we start with the first step and look for a symbol for the WFA A. We proceed like we did in the example, and we consider the true interpretation of the Hankel matrix. We use the function computed by the WFA to fill in the entries and use them to recover the negative Fourier expansion of the symbol. So we have that the negative Fourier expansion can be expressed using the parameters of the WFA. And we remark that these series converge thanks to the assumption on the spectral radius. Since the function that we obtain is already bounded, we can directly consider this as the symbol for our operator H. Now, we want to compute the function psi and the function E, which is the difference between phi and psi. The main challenge is to choose a suitable representation. To do this, we define those functions in terms of true auxiliary WFAs. The key point is to select constraints on the parameter of those WFAs to leverage the properties of automata while still keeping the formulation general. So we define the first WFA A hat with a number of states j greater or equal than the target size of the best approximation. And we want for these two properties to hold. First, we want the automaton E to be minimal. Note that the function that E is computing corresponds to the difference between the function of the original WFA A and the one of A hat. The second condition is that 1 cannot be an eigenvalue of the transition matrix of the automaton A hat. Both these conditions will be required in our contribution. So using the parameters of the automaton A hat and the constant C, we define the function psi. The idea is to find the parameters of A hat so that psi is the best approximation described by the AAK theorem. Note that the poles of psi correspond to the eigenvalues of A hat. So the second assumption we made guarantees that psi does not have any poles on the unit circle. This is a necessary condition to apply the AAK theorem for the symbol, because psi need to have a component which is bounded, so no poles on the unit circle are allowed. By construction, thanks to the first assumption we made, the same holds for the function E, defined from the parameters of the automaton E. Now, the AAK theorem for the symbol gives us information about the infinity norm of E. The idea is to rewrite this constraint in terms of the parameters of the WFAs. This allows us to recover, after a bit of algebra, the coefficients of A hat. So now we are at the last step, and we need to be careful, because A hat is not the best approximation. In fact, if we remember the AAK theorem for the symbol, we have that the function psi can be written as L plus G. So we need to extract the rational component associated to G. Intuitively, what happens is that A hat is too big. So how do we isolate the rational component? Well, we have defined the WFAs and the complex functions so that the eigenvalues of the transition matrix correspond to the poles. The rational component G has only poles inside the unit disk. So to extract the rational component, we block diagonalize the transition matrix and order the blocks with respect to the eigenvalues. We are interested in A hat plus, which is the subblock having all the eigenvalues smaller than 1. So this way we obtain the best approximation. Finally, the approximation error is given by the singular value as stated by AAK theory. Given that the spectral norm bounds above the L2 norm, We actually obtain a bound also on the L2 norm with respect to the functions computed by the WFAs. To conclude, we applied AAK theory to weighted automata and provided an algorithm for the optimal spectral norm approximate minimization problem of a real WFA A defined over a one-letter alphabet with spectral radius of the transition matrix smaller than 1. The next step for future work will be to extend the result to the multi-letter case and to other classes of models. A first step in that direction has been to extend our solution to the more general setting of black boxes for language modeling, in which the rank of the Hankel matrix can be infinite. So the big missing step will be to extend this work in general for any alphabet with more than one letter. Thank you for your attention and have a great day.